Alrighty, still looking at circular motion. A few little aspects that we want to discuss here, and then we'll get into some slightly more complicated bits. So we've looked at it and we found that centripetal velocity or centripetal acceleration is equal to velocity squared divided by radius. And that was a pretty strange formula. Our acceleration in the past was just like that, right? So for a given circle, going around in a circle if you like, let's have a look at this situation. If we went like that, right, and we're saying, okay, we've got a 5 meter radius and we're traveling at 5 meters per second. It's quite fast, really. When we look at the circumference of that circle, 2 pi r, then we've actually got 2 pi, let's say 6.28 times r, which is 5. We've got 31.4 meters, so quite a big distance. Now we're going at 5 meters per second, right? So how long will it take to get around that circle? So time to get around the circle is equal to distance, 2 pi r, divided by velocity, right? So that just comes from this formula: velocity equals distance over time. So time equals distance over velocity. So we just go 31.4 divided by 5. And we end up with a time of 6.28 seconds. That's the time. And so that could be called our period, right? Is 6.28 seconds. And I think you've all known that, or should know from waves, that the period is the inverse of the frequency. So the frequency would be 1 over 6.28. If we've got that on our little calculator here, we can use that button x to the minus 1 for the answer. And we get 0.159, so we could call that 0.16. So F could equal 0.16 hertz. And that's how many times does it go around a second? Well, it takes more than 1 second to go around, so it's only 0.16 hertz. That's its frequency. And the period was the time it takes to go around. Now, looking at that formula here, A equals V over T. So T equals V over A is legitimate, isn't it? Don't you think? But what's A? Well, if we've worked out our A with our centripetal calculation, we come up with a number. None of this is going to work, right? So what is our A for the circuit? Well, it's V squared over R, which is 5 squared, that's our V, 25 divided by 5, right? Our velocity is 5 meters per second, our radius is 5. So it's 25 divided by 5 equals 5 meters per second per second. So that's our centripetal acceleration. Now, if we did this here and we said, oh, okay, I've got my velocity, it's 5, and I've got my acceleration, it's 5, I'd come up with a period of 1 second, right? Which is totally absurd. We worked out that the period was 6.28 seconds. So don't mix up your formulas. If you're going in a circle, your centripetal acceleration is absolutely done with this formula here. All right, and this formula here is for when your velocity is changing at a constant rate, then you can work out a time. It's not for a velocity that's changing direction. This is for a constant rate of change of velocity in a linear direction. And that's not happening here. All right, so got to be quite clear whether you're dealing with motion in a straight line or circular motion. Now, a couple of things we haven't talked about are where does this force come from? So it depends what we're dealing with. If we're talking with the Earth and we've got a satellite going around, then where does the force come from to go in a circle? And I think you're all probably shouting, it's gravity, sir. F/W equals mg. And that's true. It is the gravity force that supplies the centripetal force. Now, doesn't gravity just pull an object down back to the Earth? Well, it would, but if we've got a velocity like that, tangential to the direction of that force, then that force can be used to change the direction of the object. And if you get the velocity here exactly right, where all the gravity force is used up to change its direction, then none of the gravity is going to pull the object towards the Earth. It's just going to be used to keep that object going in a circle. So that's really interesting. So gravity in that situation. What about when you swing something on a string and you swing it in a circle? Then it's the tension in the string that supplies the force. What about a car? This is looking from above. A car just going around a bend. So we've got our two lanes of light. We've got a little car, he's coming along, and he's going to go around that bend. Now, to go around a bend, you're going in a circle. You need a centripetal force towards the center. Where's it going to come from? Well, it doesn't come from your reaction force on the ground. It must come from the tires. Your car pushes against the road this way. The road pushes against you this way. All right? So the road provides the centripetal force pushing on the car, and it pushes towards the center here. So that's where, if you had no friction between the car and the road, you could not go in a circle. Decrease the friction, you decrease the amount of force that can be supplied as a centripetal force. What happens when the centripetal force disappears is all objects will continue in a straight line, as Newton said in his first law, and carry on in a straight line. No centripetal force, no can turn in a circle. All right? The car would just keep going in a straight line, according to Newton's first law. That's what happens when the centripetal force is turned off or it can't be there for some reason. Okay, I think that's enough for that little one.